yesterday we're giving some very introductory uh, discussions on dissipative quantum systems. We had some very preliminary introduction to what dissipation is all about. We haven't quite started on quantum. Uh, Today I'm going to do everything on the blackboard so that you can be more relaxed. Actually, I haven't really got started on the topic. Therefore, whatever I said yesterday, I'll again relate back from today's discussion. So our task today would be to provide a derivation of the Langevin equation, but now in the quantum domain. So whatever we did in the classical case yesterday would ensue as a special limiting situation for the quantum Langevin equation. So I must say a quantum Langevin equation because there may be several other ways of doing it, or a derivation. So our starting point is actually the Swansig Hamiltonian and its quantum version. So recall Swansig, this is Bob Swansig, 1973. And then subsequently there were papers in the quantum domain by Ford et al. A series of papers from 1984 onwards where they essentially use the same model. So the model is that you start from a Hamiltonian. You can either do it from a Hamiltonian mechanics or Lagrangian, doesn't matter. And so what you think is that the picture that you have in mind is that you have a large particle, a Brownian particle, whose mass is, let's say, m, and its momentum is indicated by p and its coordinate by q, the generalized, the canonical coordinates rather. And this is in a medium where there are much smaller particles. So this is the standard paradigm of Brownian motion as has been discussed by me, by Dr. Zava Pandit. So this is your standard paradigm. So you start writing down the Hamiltonian for this large particle. So as you know, it has a kinetic energy term, p square over 2m. But now we'll be using quantum mechanics. So I will indicate that by saying that these are all quantum operators by putting a cap on top of p, q, etc. And now you can have the particle move in an arbitrary potential that we don't specify at the moment. And then you have this coupling term, which involves a summation over j from 1 to n of a whole lot of such small particles which are connected by springs to this large particle. So you have pj squared over 2mj, mj being the mass of the jth particle and pj is momentum. And then you have plus half mj omega j squared, a harmonic oscillator kind of term, where you have, however, a displaced harmonic oscillator, Cj q, whole thing squared, and you insert a term here so that when you do the cross term, that term would actually give you a linear coupling. So you have an mj omega j squared. The idea being that when you complete the square, the cross term would have 2qj cjq over this term. So that will cancel this, and therefore you would be left with a linear coupling of the form summation j cj qj q. That is to say that this is an interaction energy which is linear in the coordinate of the particle of interest and also linear in the particle which is part of the heat bath that we're going to consider later. Okay, so you see this is a time independent Hamiltonian as you would use normally in quantum mechanics, and therefore you can start using ordinary quantum mechanics to write down the equations of motion for governed by this Hamiltonian. So as you would know that you first write down, let's say, P dot. Okay, let's first write down Q dot. So dot is the time derivative, if you like, you can use dq dt. So that's equal to the imaginary I over the Planck constant times the commutator of h with q. All right? So now you look at the q. So the only term that will not commute with q in the Hamiltonian is this term, right? So you have p square over 2m, commutator of q, and you know how to do this commutator very easily, right? I mean, for instance, p squared commutator with q is p squared q minus q p squared, and what you do is you symmetrically add and subtract. So you have basically added 0. Okay? And so you have p times pq. You take these two terms, pq minus qp, and then you take that term, you get pq minus qp, right? Right? And that's just the commutator of p with q. It's just a commutator of p with q. And p with q is simply minus I h bar. So the net result is minus 2 I h bar p. So when you plug it in, this 2m will the 2 will cancel, and h bar cancels, and there's an I there, so that will kill the negative sign, and you have p over m. Is it okay? Yeah, there are several ways of doing it. Right. It's okay? Please do ask if you have any question, all right? Yeah? This one? This one? Which one? Even the Hamiltonian structure? I should explain to you? I can't hear you. Would you be loud a little bit? Huh? This term? Are you asking about this term? This term? This term? पापा ठीक से बताओ ना कौन सी वाला full expression or which ones are you asking about? Which term are you asking about? Pura. Pura. This is called kinetic energy. This is the potential energy for the particle of interest. Is there any confusion there? Huh? Yes or no or what? You tell me, is there a confusion up till this point? Otherwise, फिर बोलेगा पूरा बोला. For this particle, if this particle moves in an arbitrary potential, this is its kinetic energy and this is its potential energy. The sum of that forms a Hamiltonian. Okay? Right? Now, I have j number of little particles. So forget about the sum. Take just one, jth particle. Okay? So this is the kinetic energy of the jth particle. What's the issue? So this is like this term, kinetic energy of the jth particle. Okay? And now you assume that the jth particles are like harmonic oscillators. So for harmonic oscillator, you have an energy which is like half m omega squared q squared, in this case qj, all right? You have seen this before, harmonic oscillator? Huh? Except that we are saying that they are all displaced harmonic oscillators because we are saying that each of these jth particle is coupled to the large particle by a spring. And therefore, the net displacement with respect to any origin, if this is q, then that small distance is qj minus capital Q, or qj minus little q, sorry. So that is this term. With some coupling constant I have put in for my own convenience or Swanson's convenience, which is such that when you complete the square, you get a linear term in the coupling. So all I have done is to embed a large particle in the milieu of a whole lot of other particles which are harmonically bound to this large particle. Now you tell me. Okay. Any other question? Okay. So now Q dot is easy. What about P dot? So P dot is similarly the commutator of H with P. So P, of course, would commute with this term. P does not commute with that term. So we have a term and what are other terms that P does not commute with? Avas? Huh? This term. Because there's a Q sitting there. But of course, P commutes with Qj. There's no issue there at all. It's that P doesn't commute with this guy. So it's simply P with Q, except that I have a factor there. No, sorry, I have to square it. So let me do it slowly. So it's Qj minus Cj Q over Mj omega just squared. That's it. Okay? So this is what we have to do. Now, do you know how to calculate the commutator of an arbitrary function of Q with P? Quantum mechanics, have you done it? Yes, no, maybe. Okay, so then we do what our friend was saying. What you do is, okay, I do it on the side. Operate it on an arbitrary function of Q. All right? So what do you get? You get U of Q. Let me not write the hats for the sake of simplicity. And then you have P, U of Q, F of Q. Right? Now in the coordinate representation, what is the meaning of this operator? Huh? Say it loudly. Good. So you have a minus IH bar, U of Q. Well, I don't need a partial. Okay? All right? So I have two terms here. I have u prime of q, which is the first derivative of u with respect to q times f, plus I have u times df dq. There's a minus sign here because there was a minus sign here and p was minus I h bar. So you can see that this term and that term actually exactly cancel each other, and you have minus I h bar u prime of q times f of q. Therefore, this operator operating on an arbitrary function has given this number times that same arbitrary function, and therefore the answer of this term is given there. And so now you have, which is the derivative of u with respect to q. The prime means du dq. Okay? This is something you would immediately expect, because even in classical mechanics, the rate of change of momentum is proportional to the force. And the force for a conservative system is the negative of the derivative of the potential. That's the first term. Quantum mechanics is no different, right? Except that when you use these equations, you have to be very careful about the order in which you put p and q, because as we indicated there, p and q do not commute with each other. All right? Question? Qj minus Cjq over mj omega j squared, whole thing squared, p minus p times the same thing. Okay? And so the question is, what does this thing do if you operate on an arbitrary function f of q? So again, you get this terms times p minus this, which is going to cancel for the reason I mentioned earlier. And what you're going to be left with is minus p, which is IH bar del del q of qj minus cjq mj omega j squared times f of q. Is it okay? Because I have done the same kind of cancellation as we did before. All right? All right? Yeah? No? It actually follows from there. That's absolutely good. Thank you. It follows from there because in any arbitrary function it would be like that. So you simply take the derivative of that, and that's what we're going to do now. So you get IH bar 2, sorry, this is Q, times minus Cj over mj omega j squared times f of q. So therefore, the net result is plus I over h bar summation j half mj omega j squared times this result. So you get 2 IH bar. This guy is going to cancel with that, giving you a negative sign. And then there's a negative sign before, so it gives a positive sign. And you get a Cj times Qj minus Cj over mj omega j squared. And this mj omega j squared is also going to cancel with that. So let me clean it up a little bit. So you have minus u bar of q plus summation over j Cj Qj minus Cjq over mj omega j squared. Is it clear? Just check. Yeah. Is it clear? So as she pointed out, lady, that basically it's the same thing, that for any arbitrary function, view this as an arbitrary function of q, and all that we have done is to take the derivative, the negative sign. Except that we had to cancel some of those factors. Okay? Okay? Can I proceed? So let me, I think I need some blackboard space. So I rub this off. And only in a quadratic structure in the equations of motion. That's the generic result for harmonic forms. So next thing to do would be to write down the equations of motion for the small particles. So for the large particle, you can see that its momentum equation is actually getting coupled to the coordinate of the small particle. So you're going to get coupled differential equations to solve, right? Operator equations. So now you do the qj dot term, and that's simply pj over m for the same reason as before. And more interesting equation is, of course, the equation for the momentum variable. And that is basically, you have to start taking the commutator of this term with pj. So that's going to be, so pj dot. And now you see, okay, so let me do it slowly. I want to do things a little slower than you can proceed, because you have seen all these things before and most of the other people have not. But since I need pj, I have to consider an arbitrary, a fiduciary j prime term, and look at the commutator of that with pj. Okay? So though, this is squared. Though, now pay attention now, though qj will not commute with pj, but qj prime, of course, would commute with pj, because they refer to two different particles, right? Hence, when you do this commutator, you're going to get a Kronecker delta between j and j prime. So I might as well forget about the summation over j, okay? Right? There will be no sum. Only the j equal to j prime term will contribute to this commutator calculation. And when you work it out exactly the way we have done this before, the answer that you would get is minus mj omega j squared cj times qj minus cjq over mj omega j squared. Somebody check this out, Aras? There's no CJ? Or when you take a derivative of this, don't you get a Cj out? Huh? When you do delta Qj of that, maybe you're right. Just let me just check. I get 2 Qj minus Cjq over mj omega j squared. And then I have then the delta Qj over K is simply 1. You're right. Thank you. You have to remember this, that you see Qj dot gives you Pj, right? So Q and its higher derivatives do not commute with each other, right? Because Q and Q dot gives you P, they don't commute. So in quantum mechanics, they don't commute. So you have to be careful about the way you do these operations. But actually, the results follow exactly the way the classical calculations go. So essentially, you have to solve the second order differential equation, which you obtain by taking a further time derivative, and for Pj dot plugging in from this result. So you see, if you remember, yesterday I did it in a hurry because I was showing you stuff on the PowerPoint. But essentially the same equations were there even in classical theory. There's no difference, right? Whether you use Hamilton's equations of motion in classical theory or Heisenberg commutators, you end up with the same equations. Only when you solve them, you work with them, you have to be careful, as we will see now. But first of all, you immediately know, and this is a solution that we wrote down yesterday for the classical case also. This is a harmonic oscillator equation. And that solution, as you would guess, is that Qj of t is equal to Qj at time t equal to 0 times cosine function of omega jt plus Pj at time t equal to 0 over mj omega j sine omega gt term. So that would be your ordinary harmonic oscillator solution for Q. All right? But now because of the coupling, you get an additional integral term which has a structure of, if I have done my algebra correct, and ours can check, is that you get sine of omega j t minus t prime. This came from the cross term. So let's just pause and check if this is indeed the solution. So take time t equal to 0. You set t equal to 0 here. The right hand side you get 1 here, so which is so far so good. This term will vanish because sine function goes to 0 at time t equal to 0. This integral is identically 0 because in the upper limit you put it equal to 0, it vanishes. So that part is satisfied. Then you start taking time derivatives. You take one time derivative Qj dot. Let me do it like this and then you can check. Qj dot, you get a minus omega j from here because cosine function taken derivative of will give you minus sine with a minus omega j. And here you get a plus omega j Pj of naught. And here you have to do an integral over, so first of all there's a There's a sine function here, so that will also give you a cosine. And then when you take the derivative under the integral, when you put t equal to t prime, that term actually disappears. And then you take another time derivative, and you can check that you get back to this solution. Okay? Maybe in the tutorial we can do that if you still have not done it. Minus Cj q at naught mj omega j squared times cosine, where I have actually used the equation of motion for q itself also, cosine qj of t plus pj of naught over mj omega j sine omega j t plus this integral term, which is Cj over mj omega j integral 0 to t dt prime q of t prime sine omega j t minus t prime. So this is what we need to substitute here to obtain an equation for the tack particle momentum. So the tack particle momentum has this Newtonian term, and further I have summation j equal to 1 to n Cj, and this whole bracketed term. Okay? I'm going to do something to this term, that's why I'm not writing it down again. Okay? All right, so far? Okay, now let's just focus on this term and do an integration by parts. So this integral 0 to t dt prime q of t prime sine omega j t minus t prime can also be written as q of t prime times cosine of omega j t minus t prime divided by omega j minus okay? This one is q hat 0. This is q of t, that's q hat 0. Where did it come from? I solve for qj and I subtract, let me work it out in the tutorial, okay? Hmm? No, I'm right, but I'll have to just check. Because you have to solve this initial condition that when you put t equal to 0, you must get t equal to 0. So I'll just check later on. Maybe it could be that here itself I made a mistake, but we'll check on that. But this is correct. Let me just check it again. Check. Actually, you are right. It is not there at this stage. It comes from this. It comes from that actually. So I should not have. this term comes after the partial integration. So let me not write this term. So it is this term that I'm massaging now. So what happens is, yeah, now I get. So you see, when I did this partial integration, I get q of t over omega j minus at t equal to 0, so you get q of 0 over omega j cosine omega j t. So that's this term, all right, after the partial integration. So after the partial integration, the term that we're going to write down is, okay, minus 0 to t dt prime, and this is dq dt prime, so it's p of t prime over m times cosine omega j t minus t prime divided by omega j. Let me clean it up a little bit. I think I owe that to you. So this term is correct, okay? This solution is correct, and now in this term I'm doing a partial integration. So this partial integration I've shown here, okay? So when you do the partial integration and put the limits, you get a q of t over omega j here. So that's going to be here, except that I have to still have, this is mj omega j squared. Do I have an extra omega j somewhere? Hmm? Yeah, right. So that's what gives you mg omega j squared. Yes, right. You have mg omega. No, sorry, here. Cj over mg omega j there. So you get Cj over mg omega j. That omega j gives you Cj over mj omega j squared q of t, and that's this term. Okay, Abhishek? And from the other limit, you get the term at q equal to 0, and that's this term. Okay? And this term has disappeared, and after the partial integration, you get the structure like this. So let me just write down this. So you have Cj. So the Q equation has, in the curly bracket, j equal to 1 to n, Cj times the solution of this equation, which is given here. So I have to write down the right-hand side. So I get Qj of naught minus Cj Q of naught over mj omega j squared cosine omega j of t plus Pj of naught over mj omega j sine omega j t, curly bracket doesn't yet close. That's Cj times this, and then I have a further term, which is minus do you have a minus? Yeah. Minus integral 0 to t. Now, as Abhas said, that there is a factor there. Okay, so I have a factor Cj over mj omega j. So an extra factor of Cj over mj omega j times P of t prime over m times cosine omega j t minus t prime, curly bracket closed. Okay? Let me rewrite this term as p dot as minus u prime of q minus an integral over 0 to t dt prime p of t prime over m, and I'm going to introduce a function zeta, which I will define shortly, zeta of t prime. Oh, sorry, this is zeta of t minus t prime, yeah. Plus, well, eta of t. So what is my definition of zeta of t minus t prime? That you simply read out from this term. So zeta of t minus t prime, or zeta of t, let us say, is defined to be, you just read it out from here, summation over j, cj over mj omega j times cosine omega j t minus t prime. Should I get a squared? Yeah. There was a cj outside, so I get cj squared. And for some reason, I must get an mj omega j squared. That is because there was an omega j outside, and there was an omega j inside, so that gives you omega j squared. So that's zeta of t, and eta of t. Can you read it from there? Can you read what I'm writing here? No. So let me write eta of t upstairs here. So eta of t is written here. It's summation j equal to 1 to n cj times qj naught minus cj q of naught over mj omega j squared times cosine omega j t plus pj of naught over mj omega j sine omega j t. Okay? So you gaze at this equation for a while and discover that this is a structure of a Langevin equation, right? Because if you remember, the Langevin equation that we wrote down yesterday in the classical case had p dot equal to minus u prime of q, that's the Newtonian term, then minus some gamma friction coefficient times p of t, plus I was using a notation theta of t for noise. So we don't quite have that. What we have, instead of a constant gamma, constant friction term, we have a memory kernel here, all right? And we have a term which we are going to call a noise term. Quote unquote noise, and that is because that yesterday we were introducing noise from outside by hand. And we said, we modeled the noise. We said that the noise as well as the systematic component of the drag force, the viscous force, have the same origin, namely the collisions that the large particle suffers from the surrounding smaller particles. So the cumulative effect of those collisions have a systematic component which you modeled a la Stokes, and the rest is pure noise. And then there was some question about the meaning of averaging over noise with this time average, ensemble average, etc. Today, by this very definition, you see some of these questions would be resolved, because if we are going to interpret this eta of t as noise, you can see the noise is actually now an operator in quantum mechanics, because the noise is in fact dependent on the initial values of the coordinates of the tagged particle as well as the surrounding bath particles and the moment of the bath particles. So they live in this large Hilbert space that comprises the particle of interest as well as all the other many-body system of the large particles. It's a large Hilbert space, and they're like your dynamical degrees of freedom. And when you treat these dynamical degrees of freedom a la statistical mechanics, they are like noise, but they're like, the noise that originates due to thermal fluctuations in the system. Like the velocity of a Maxwellian gas is noise, or like the current flow in a resistor which gives you Nyquist noise is a noise, okay, because the electrons, the motion of the electrons is a noisy one, okay. So in stochastic processes, you use the concepts of random variables, as has been done by Dr. Sabha Pandit, either in the coin tossing problem or the random walker problem, or let's say the spin kinetics of an easing model a la Glauber kinetics or Kawasaki kinetics, whatever that you might be familiar with. And there you use stochasticity explicitly. Here we are taking the route of going systematically from the Hamiltonian dynamics into statistical mechanics, following the Gibbs procedure, all right? And there, the noise is now explicitly living in the Hilbert space of your large system. You have a large system because you have an embedded particle harmonically bound to a whole lot of other particles. We are going to, what you have done is you have projected out or have integrated out the degrees of freedom of the smaller particles by integrating the jth particle equations of motion. And having projected them out, the projected dynamics of P actually is looking like a noisy equation. Okay? So the way, and this is exactly the way you do derivations in equilibrium statistical mechanics. If you try to remember how you calculate or how you derive the form of the partition function, you say that you have a system of interest and you have a replica of similar systems with which this guy is in interaction with. They exchange energy, but then you say that this replica of all these systems constitute, they're like ensemble of a collection of same systems, and they're at a constant temperature T. So you fix the temperature by this Lagrange multiplier method, if you think of the derivation of the partition function. So beta emerges as a Lagrange multiplier, which you interpret as temperature, and that's how you get the partition function as exponential minus beta times the Hamiltonian. So you're using the same idea, that what you're going to say is that you have a large blob of particle which may have arbitrary initial conditions, like the ball I was dropping to the jar of, as Professor Jayanta Bhattacharya pointed out, has to be a jar of glycerine and not water, because otherwise through water it will fall off very rapidly and you'll not get the terminal velocity so quickly. So let's say a jar of glycerine, and that jar of glycerine is like your small particles, which when they go into the thermodynamic limit of an infinitely large system at a fixed temperature T, we have not introduced temperature yet, at a fixed temperature T, so that it's such a large system that your ball is having interactions with it, is going to, its own equilibrium is getting disturbed, is also going to minutely disturb the equilibrium of this large system, but it is so large that there are so many channels of dissipation of energy that the temperature of the large system does not get altered. And that's the meaning of a heat bath in thermodynamics and statistical mechanics. Okay? So same kind of assumptions we're going to invoke, and therefore you can see the logic of how to get irreversibility out of a system which is manifestly reversible. You have integrated equations of motion in the forward direction. You have projected out the other degrees of freedom. Then you're going to go to the continuum limit where summation over j is going to be replaced by an integral over a suitable weight function of the frequencies of these oscillators, like you do in the Debye model of specific heat for a solid when you calculate the phonon contribution to the specific heat. Same kind of ideas. And so you're going to have then this system to be a very large system. And then you're going to invoke temperature, where you would have something like the analog of equipartition theorem, which you're going to work out, where you would calculate correlation functions of the noise and how that gets related to this kernel that sits in here, the memory function or the memory friction term. So that's the whole strategy. Yeah, Rajesh. Sorry? I don't know, because it has a you see, if it did not have a memory, then t prime will fold into t. This function remembers the entire duration of the integral process. This t prime is going from 0 to t, okay? So t is larger than t prime, but this function tells you what happened in the past. And I guess that's why it's called memory kernel. Sorry, Suparna? Yeah, it remembers the past, that's why it's called memory function, yeah. I think it is correct, but we will take a bet afterwards. Be that as it may, this is correct, okay? And then we'll work it back. That has to be then checked, yeah. So seriously, you have any question? Theta p squared going from minus infinity to infinity will give you what? Okay. This is also 0, because that's the quadratic form, average, huh? So noise has this property satisfied, that eta bar of t is 0, right? Second thing you have to check is eta of t prime bar, which is a correlation function. So when you do, this is where you have to do a little bit of mental gymnastic. You have eta of t, and then you have taken eta of t prime. So you're going to get the identical term, except that t prime will appear there. And then you take the product, and then do the averaging. When you do the averaging, the cross averaging of q and p will again give you 0. Okay? So you're going to only get the square of this term and square of that term, right? And cosine omega j cosine omega j t prime, and sine omega j sine omega j t prime, right? So you're going to get very good question. So let's dwell on this a little bit. Yes, Sanjeev? This one? Yes, yes, yes. Yeah. Q dot is minus omega squared q when you look at harmonic oscillator equation. So is that the confusion? Oh, kahan chala gaya wo? Haan, that was the confusion. Okay. MJ nahi tha wo. ठीक. Yeah, so harmonic oscillator equation. Q dot is minus omega squared q. I added an extra m there. Sorry. Thanks, Abhishek. So now you take eta of t prime. So you're going to get, again, see, you should get j and j prime, right? But j prime has to be equal to j, because when you do the averaging of for j not equal to j prime, they'll all be again equal to 0, right? So you're going to get a summation over j cj squared qj of naught minus cj q of naught, I don't need these hats, mj omega j squared, and then average of that cosine omega j t cosine omega j t prime plus pj of naught squared over mj omega j squared, and cj is sitting outside, sine omega j t sine omega j t prime, correct? ठीक है? अच्छा. And now you got to do the averaging. Okay? So if you assume, which is what I said, that these small particles constitute a large heat bath at a fixed temperature T, then what is P squared average? Batao, what is P squared bar? The average kinetic energy is half kT. Huh? So P square is mkt. Okay? So this guy is mjkt. And this fellow, remember harmonic oscillator. Harmonic oscillator, there is something called VDL theorem or something, right? That half m omega square q square average is the average of the potential energy, which is also half kT, right? So therefore, this average, this bar, is going to give you kBT over mj omega j squared. So this one mj, cancel this mj, and I should have got a cj squared here. Or there is, what happened? Yeah. Huh? There's a cj squared. So the net result is kBT summation over j cj squared over mj omega j squared times cosine of omega j t minus t prime. Right? What's your name? Huh? Tanmoy. So Tanmoy, now you see that the correlation of eta is your Einstein factor kBT, Einstein factor that Dr. Sava Pandit again worked it out today, times the structure of that is simply the zeta function, right? So it's zeta of t minus t prime. That's your Einstein relation or fluctuation dissipation theorem, right? The noise correlation actually is related to the systematic damping kernel. That's your inner consistency of statistical mechanics. Because what is systematic damping and what is noise? They sit in the same Hilbert space of this large particle system. And it's only after coarse graining you have taken out a piece which you call noise, and the rest you're going to call systematic friction. Okay? So far so good, all right? Do you follow this? This is still in classical mechanics. All right. Now, in quantum mechanics, we're going to get a similar thing, except in classical theory, the way this Langevin equation is formulated, if you remember, we said that theta of t prime is, let's say, gamma kbt, and it's usually a delta function in time. It's for Gaussian noise, all right? So we still haven't got a Gaussian here, right? So there is something called an ohmic dissipation model, where when you go from this finite system to an infinitely large system, you're going to replace the summation over an integral over an appropriate weight function for the density of states. And for the density of states, you assume what is called an ohmic dissipation, which is also the same form as the Debye form of phonon dissipation in phonon dispersion in when you calculate the specific heat in solid state physics. And then you will see that there's a limit in which the zeta function becomes a delta function in time. Okay? That's the classical theory. We'll work that out also. Tanmoy. Now, question to you. You see, when you do the quantum generalization, these etas, these guys are quantum operators. So let me ask you, would you ever get a delta function in time in quantum mechanics? Can you ever get a delta function in time? Yes, no, maybe? Even if you assume ohmic dissipation, just to say, no, anticipate in the future. See, what is the property of a delta function, delta t minus t prime? It's symmetric under the interchange of t and t prime, right? Because delta of t is the same as delta of minus t. So even if you interchange t and t prime, the structure of the delta function does not change. It's a two-sided delta function. Now, will that be in conformity with quantum mechanics? See, we are dealing with time-dependent operators. So the question is, if I take the momentum operator at time t and the momentum operator at time t prime, all of you have worked with the Heisenberg picture of quantum mechanics. Now, do these things commute with each other, or does the Hamiltonian commute with itself at different times if it is explicitly time-dependent, Hamiltonian? They don't. They don't. So therefore, you're never going to get a delta function in time. Okay, I don't know whether Dr. Sabha Pandit is going to discuss this. The structure of the delta function of the noise is very important to suggest that the underlying stochastic process is a Markov process. And deviation from delta function in the noise means that a quantum system is never Markovian. The reason being, and this is something that I think we should discuss very physically, that you see, see KBT, what is KBT in terms of dimension? Huh? Energy, very good. So when you divide by h bar, what do you get? Dimension of frequency. So inverse of that is it has a dimension of time. Okay? So tau q is h bar over kBt. So this thing you may call a quantum time scale. All right? So what is happening is that as you go down to very low temperature, this time scale becomes longer and longer. Okay? Right? Which means that quantum effects are very important within that time scale, and that time window becomes longer and longer the lower the temperature is. But at room temperature, this time scale is so tiny that quantum fluctuations are averaged over very quickly, and therefore you can use classical theory. So what is the meaning of these quantum effects? See, the point is that quantum mechanics deals with phase coherence. That's why you see interference. That's why when we talked about diamagnetism or precessional motion of an electron in a magnetic field, that's quantum coherent motion. Or tunneling back and forth in a double well is a quantum clock. It's like a quantum coherent process. Quantum mechanics has phase coherence. And statistical mechanics or thermal fluctuations bring in decoherence or noise. And it's this interplay of coherence and decoherence that is very important in the dissipative quantum systems, because you have coherence on the one side and dissipation leads to decoherence, which are very important concepts today in the context of quantum computing, qubit, and of course in the condensed matter physics in many, many contexts. So therefore, there is a time scale tau q within which, this is a tiny time scale of course, but not at very ultra low temperature, you have coherent effects still prevail, and coherence means that you cannot have Markovianness, because Markovianness is completely an incoherent phenomenon. Because a Markov process is a two-step memory process in the context of, let's say, random walker, and so decoherence means that that memory is completely lost. So therefore, you will see that, I don't know whether we can still do it today, that when we calculate the correlation function of the noise, we'll get something like this, and even when you go to this ohmic limit, this function will never be a delta function in time, although the memory kernel will fold and will give you a constant friction. Okay? So we'll see that now. Any question? Basically, what is happening is that see, in quantum mechanics, and also in quantum statistical mechanics, you have to calculate in quantum mechanics a wave function which is e to the minus iht over h bar times psi at time t equal to 0. And in quantum statistical mechanics, you have to calculate a partition function which is stress exponential minus beta h. Right? Right? Now, this h is t plus v, or t plus u. I've been using u. The problem is that t and u do not commute. So e to the, see, everywhere you actually have to deal with an exponential of a Hamiltonian operator. This operator is a very large matrix, infinite dimensional matrix. Therefore, none of your computers will be able to handle that. In classical mechanics, the problem is simpler, because when you take e to the iht, it is minus e to the itt, e to the minus iut. And now you massage that separately. It is just p squared by 2m, and in statistical mechanics, you have the same thing. And you can average over a Maxwellian very easily. That gives you a prefactor in the partition function, and you're just left with that, right? So this could be like an Ising model, where you don't worry about kinetic energy at all, right? This you cannot do in quantum mechanics anymore. So kinetic energy and potential energy are inexorably mixed together, okay? So you develop some tricks. The tricks are actually you write this in a Trotter formula and use the Feynman path integral formulation, where you say you break this up into tiny, so there are many paths in quantum mechanics, and you break them up into small segments, and it is such that there is a property that two non-commuting operators, you still have e to the a, e to the b, and then there are correction terms which are multiple commutators, nested commutators of A, B, et cetera, et cetera. So if you have a small tiny element, because you're going to have time t here or beta here, beta is the inverse temperature. So when you take small time segments, these multiple commutators will have delta t squared, delta t cubed, etc. So you ignore them, and over short time segments, this is the Feynman idea of path integrals, you could still do this computation, and this is what you use in quantum Monte Carlo. Except the problem arises that when the temperature becomes very small, you need to go to very, so the time becomes another dimension, and the time t scales like, because in calculating the partition function, you do an imaginary time calculation of path integral. So t is like I h bar beta, and so when you go to zero temperature, near zero temperature, that time axis becomes very large, and in the thermodynamic limit, that time t axis also becomes infinitely large. So a three-dimensional quantum system is actually behaving like a four-dimensional classical system, where time t is the other axis which goes to infinity, and if you don't have infinity, they'll have finite scaling, finite size scaling effects, et cetera, et cetera. So now there are situations, so let me just say that quickly to motivate you, that, for instance, we just mentioned the Ising model. Now, the Ising Hamiltonian is minus some ij, you can take nearest neighbor, jij, sigma I, sigma j, but usually they're the z components of the spin operators, right? It's a completely classical system, because once you have diagonalized, or once you have chosen z as your axis of quantization, the problem is that is essentially a combinatorics problem. That's why if you look at the Ansager solution, there's nothing, no quantum mechanics there. So I guess you might have worried about it, that when you calculate the partition function for this problem, you don't have to take t into account at all. The t is not there. This is the u. That's your u of the problem. However, suppose you are mischievous and you add another term, which you can do in the laboratory actually today. There are many physical examples where you can do it, that you add another field term in the x direction. Now this is called a transverse Ising model. Now you have a problem, because sigma x does not commute with sigma z. So this transverse term does not commute with this other term. So this transverse term is like a kinetic energy term, okay? Because it can make transition possible between the eigenstates of sigma z. It mixes up the eigenstates. So now you have a difficult problem to do. And this model has an interesting phase diagram that suppose you plot the transverse field gamma along the x-axis. No, sorry, you plot it along the y-axis, the transverse field, and the temperature here. So when gamma is equal to 0, this term is not there. You have the pure Ising model, okay? And all of you know that this Ising model in dimensions more than 2 and above exhibit a phase transition such that here is a critical point, Tc, and this is for gamma equal to 0, above which the system is paramagnetic, and below which the system is spontaneously ferromagnetic. That's the Ansager solution of the 2D Ising model. Okay? So there's a phase transition. But now you think of jacking up gamma. So what is going to happen is, see, if you view this in a mean field sense, this term is like a sigma z term in an effective field, which is also along the z-axis, but is, if you look at the ith spin, is proportional to the z component, the jth spin. So you have an internal field along the z-axis, but then there is another field now along the x-axis. So your resultant field is somewhere in between. You have lost your quantization axis. And as you go on jacking up gamma, what is going to happen is that there is a line of critical second order phase transitions. You go like this. The critical point decreases. The Curie point goes on decreasing until you reach a certain threshold value of gamma, where gamma is so large and the torque is so large that you have tilted all the spins along the x-axis, and you get here. Okay? Now this is a special point where the temperature T is equal to 0. So to answer your, or elucidate on your question, then all these statistical mechanical fluctuations that you incorporate due to temperature are no longer there, but you have a phase transition because up till this point, this value of gamma, you still have a ferromagnetic phase, but then beyond this value of gamma critical, your transverse field is so large that you have lost that phase transition as far as the order parameter along the z-axis is concerned. So that's a quantum phase transition, and much of our modern condensed matter problems have to tackle with the behavior of the system near such a quantum critical point. So that's the quantum critical point, and that's governed by quantum fluctuation. And that's why quantum fluctuations are so important. And that's why we were discussing dissipative quantum systems, because you can ask the question, what happens if you add dissipation to this transverse Ising model? There's a lot of work in that area also. And that's also interesting because you can think of, those of you who do simulation or quenching, you can think of a quantum quench through the gamma, and you see how our domains and other things grow. And they would have very different scaling properties than the domains that will grow as you quench the system through the Curie point. Okay? So I guess I stop here, and in the tutorial, maybe I can clarify some of these steps and also work out what the noise correlation would be in the quantum domain for the quantum Langevin equation. Because it's 4 o'clock, really, so it's for me to stop also, right? Yeah. Is there any question? বাইরে কথা বলো তোমার সাথে। Yeah. The order parameter is n times summation I, not n. That's the order parameter. It's gamma versus T. It's a diagram in what is called the field space. They're all fields. But you can also add the order parameter here if you like.
So a few announcements.